I'm Dr. Darryl Baynes, President and founder of Interactive Science Programs. We are one of the largest science and math outreach companies in the nation, owned and operated by African Americans. And we're here today to do a science demonstration and also to show our support for Black Lives Matter. With these turbulent times we're in, we often think about the Declaration of Independence, which says we hold these truths to be self-evident, that all men are created equal. And we see that hasn't always been the truth, and that we really have to put an emphasis on the fact that Black lives matter, trans lives matter, people who have been underserved and underrepresented. All of us are facing challenges from time to time, and we're going to show examples of African Americans and people of color who have done great things in math and science despite those challenges, even overcoming systemic racism and all of the problems that we have in society. A lot of people have done great things. For myself, I grew up in Philadelphia. I used to go to the Ben Franklin Institute in Philadelphia, and I would see people do science experiments. I got excited about those experiments, but I never saw anybody African American doing the science, and I never saw any women doing the science. So I did the first most important thing I could do. I learned how to read. Once I knew how to read, there wasn't any information I couldn't find out, and there wasn't any teacher who could stop me, because once you learn how to read, even if your teachers don't teach you, you can read the information yourself and teach yourself if you have to. Let me get something to drink here real quick. That was very refreshing. Now, of course, a lot of people may look at this and think, man, he didn't drink anything. What's he doing? Well, I'm going to show you. I have some bubbles here. We'll use this one. Now, I'm going to blow some bubbles. When I blow the bubbles fall down towards the floor. Our bubbles are heavier than the air. They're falling down towards the floor. Take the top off of this. Notice our bubbles floating. There's something in the tank holding the bubble up. The material holding the bubble up is either a solid, liquid, or gas. We can't see it, so we know it has to be a gas holding that bubble up. So there's a gas in this container. I scooped up the gas in the container and I drank it. So there's a gas in this container holding that bubble up. All right, so let's think about this. In this container, we have a white solid called dry ice. And I scooped up the gas and I drank it. But most people do this almost every day because this is the gas that they use to put the bubbles in soda. So when you open a soda bottle, you hear tss, you hear the gas coming out. That's CO2 gas. Now, let's see what else we can find out about this gas. I'm going to come over here to some candles, and I'm going to light my candles. Okay, all of our candles are lit. I'm going to take this empty coffee container, scoop up our gas, pour the gas over the candles. Notice the candles went out. There was a gas in this container. We scooped up the gas. We poured the gas over the candles went out. This is a proof that a gas can flow, just like a liquid. You couldn't see it, but the candles went out one at a time as the gas was flowing down the steps. Okay, so this is a proof that this gas is heavier than the air. All righty. I have a balloon here. We're going to fill this balloon with helium. I have some helium tanks back here. Well, I have a helium tank. I have helium in this balloon. When I let the balloon go, it's trying to rise. Helium floats. Everyone knows if you suck in helium gas, your voice will change. A lot of people know what will happen, but they don't understand why it happens. The reason my voice changes is on the chart that's on the screen.
I suck in helium gas and my voice changes. But we need to think about why my voice changes. The chart says what the gas is, how heavy the gas is, how fast the molecules move. Everyone knows helium is lighter than air,
And they may think helium changes your voice because it's lighter than air, but that's not so. The reason my voice changes when I suck in helium is because the helium molecules are moving so fast. Air molecules move at 1,130 miles an hour. Helium molecules move at 3,050 miles an hour. So when I suck in helium gas, it's coming out of my mouth so fast, it's pushing the sound waves faster towards your ear, makes my voice sound higher. So let's apply that. I have a friend, he sucks in the gas all the way at the bottom of the chart, sulfur hexafluoride. When he sucks that gas in, his voice is deep. But something else can happen to him physically, and that is that the gas is so heavy at 146, it won't let the lighter air in, he could suffocate. So what can he do? He can go in a corner and stand on his hands or on his head, and the gas will come out of his mouth just like the gas ran down the steps because the gas is heavier than the air. So we're going to do an experiment. We know that CO2 gas goes down the hill, puts the fire out. We're going to have a race. I used to run track for the University of Pittsburgh, so I like having races. We're going to race CO2 that weighs 44 and C3H8 that weighs 44. They both weigh 44. We're going to race them down the steps to see which one will get to the bottom of the steps first. So let's set up our finish line. So I'm going to move these other candles. And the candle at the bottom is going to be our finish line. Okay? So let's look at who's racing. This is CO2 gas. That's what we have in here. It's a straight molecule, straight up and down. We're going to race that against C3H8 that looks like a poodle. So we're going to race dry ice gas and poodle gas down the steps to see which one will get to the bottom of the steps first. So I'm going to light my candle. Notice I asked the questions, so we come up with our hypothesis. I'm going to do CO2 gas first. Scoop it up. I'm going to count as soon as I pour. 1, 2, 3. Before I even got to 3, the candle went out. Okay? That's CO2 gas. So I'm going to light my candle again. Then I have a small container of poodle gas right here. This gas is heavier than the air, so it's not going to go anywhere. It's going to stay in my container. Okay? Okay. Now, our candle's lit. Now we're going to try poodle gas. See how fast this goes down. 1, 2, 1, 2, 3. Oh, you know what? That's my bad. I forgot to mention that the poodle gas was flammable. So that's my bad. So we can't use this to see which one will get to the bottom of the steps first because the poodle gas is flammable and it doesn't put the fire out. I'm going to tell you, they both fall down the steps at exactly the same speed because they both weigh exactly the same. But now we need to think about this, that why is one flammable and one not? If you look at them closely, notice they both have carbons, but the poodle gas has hydrogens in it. The more hydrogen something has, the more fire will give off. So it's the hydrogens that make the poodle gas flammable. So let's think about this. A flame. What does a flame look like? And fire. We have our triangle of fire. So in our triangle of fire, if we think about it, our triangle of fire has oxygen, heat, and fuel. So we're going to do a little experiment with that. So I have a candle. Put on my safety glasses. And I'm going to light my candle. Right now, our candle's burning. The oxygen's in the air. The heat is the striker to get it started. The fuel is the wick of the candle. Firefighters recognize one more thing, that's chemical reaction. You can have these three things together. If you don't have a chemical reaction between them, you don't have a fire. So we're going to start off with fuel first. Right here, our fuel is the wick of the candle. If we take the fuel away, then the fire goes out. I have a little piece of paper here. I'm going to fold this piece of paper. Everyone knows that paper burns. So I'm going to set off our piece of paper. Notice it burns very fast. That was a piece of flash paper, like when you see a magician throw fire. Okay? That's an example of increasing the fuel. Here's another example of increasing the fuel. This is a little piece of metal called magnesium. So our magnesium is burning. You see how bright it is. You can tell that this is what they put in fireworks. Okay? So these are all examples of increasing the fuel. I have one more example. That's this material called lycopodium. Lycopodium is like sawdust. So I'm going to put some in the spoon. The little pieces are very fine, really small, and it's very flammable. So I'm going to hold this lycopodium over the flame. And even though it's a very flammable substance, it won't catch fire. So you might be thinking, well, the spoon is not letting enough heat get to it. So I'll put more fire on top. Notice it still won't catch flame. If I hold it up and I sprinkle, it automatically becomes flammable. When the little pieces are in the spoon, they're so tight together they can't become flammable. Once I sprinkle it as it falls, it becomes a mist. Instantaneously, they become flammable. So this gives us an idea that the most important part of the triangle of fire is oxygen. Now, let's think about this. My fire extinguisher. It's hard to see maybe from the camera, but it says you point this at the base of a fire, you pull the trigger, fire goes out. Why does a CO2 fire extinguisher put a fire out? And it does it for the same reason that the CO2 gas in our container put the candle out. And I'm not going to tell you. We have to put things together to figure this out. And I'm going to show you. This is Lake Nyos in Cameroon, Africa. This happened in 1986. The lake was at the top of a hill. If you notice, this looks like the top of an old volcano, which is called the caldera, the round part of a volcano. They just thought it was a lake at the top of a hill, but it's really an old caldera. So underneath that water were vents that vented CO2 gas into the lake. So underneath the water was a big ball of CO2 gas. In the middle of the night, the people in the village were asleep. An earthquake came along, shook up the lake. The big ball of CO2 gas came to the top of the lake, rolled down the hill. The next morning, people came into the village. They found a village full of dead people. Okay, the next morning. 1,700 dead. There was so much gas that came out of the lake and rolled down the hill. People were dead 15.5 miles away. So there was a road that they walked up and down to the top of the hill, to the lake from the village. People who lived on the side of the road didn't get the direct CO2 gas. After 36 hours, they woke up. No brain damage, no nothing. But of course, why did this happen? It happened because the CO2 gas is heavier than the air. It rolled down the hill, moved all of the oxygen out of the village. But what happened to the CO2 gas? Because the people that came in the next morning didn't die. And what happened is that by the time they came in the next morning, the gas had come, rolled down the hill, and then it was down by their feet instead of over their head. So they walked through the CO2 gas instead of being suffocated by it. What the Cameroonian government did was stick a pipe in the middle of the lake. So when CO2 gas comes to the bottom of the lake now, it comes out of the top so it doesn't build up like it did before, so hopefully the tragedy won't happen. It's like opening a soda bottle and letting it go flat. Same thing. There are a few lakes around the world near volcanoes that this has happened at. And this is just an example of a big one in Lake Neos, Cameroon, Africa.